The next speaker is Jakub, who's going to give a short update on HelenOS.
Mm-hmm. So welcome. It's good to see so many familiar faces. In this short update talk, I will just go through the last year in HelenOS, basically from the last FOSDEM to this date. But first, a short recapitulation of what HelenOS is. So it's a portable microkernel-based multi-server operating system. I think it's fair to say that it's also a distribution of itself. So unlike some of the L4 projects that are more like unassembled Lego bricks, this is also made of Lego bricks, but assembled already. It's designed and implemented from scratch. It's not deliberately trying to mimic some other operating system or API, even though we do provide limited compatibility POSIX layer. It's written in C and to a small degree also in C++, and it's almost 100% our own code. And it's composed of very fine-grained components. I will talk about that a little bit later. So this is the main timeline of events that took place last year. So one of those big events happened in May. It was the first and also the only release last year, 0.9.1, codename Harmonia. I was once asked by Lazar, I guess, why Harmonia? The reason is that in that release, we merged the ARM64 port made by Petr somewhere there. The author is present, I guess, in this room. Where are you? Over there. And also some other ARM work, so that's why it is called Harmonia. I also participated in the L4 retreat shortly, where I worked on making HelenOS work on the L4 hypervisor on x86. In July, there was this SUSE Hack Week where some of our developers worked on implementing the standard C++ library future header. And in August, there was the biggest HelenOS event of the year, the HelenOS Camp. This time it was only 3 people, and no children and no spouses were involved, so we call it a quasi-camp. But it produced most of the topic for this talk, so it was important, definitely. So what things made it to the HelenOS master and other branches? So the already mentioned C++ future header hacked on during the SUSE Hack Week. That's already merged. Then there was a really big feature merged into master, which is the switch of the build system from the old make into to the Meson build system. That finally gave us the capability to do proper out of 3 builds. We are still recovering from the effects of from this switch, especially in our infrastructure and testing setups. That's also the reason, by the way, why there was only 1 release last year, because this, due to a a blocker, it prevented a second release. Besides of that, I work on the IPC version 2 branch. I will talk about that in just a couple of seconds. Martin Dětský worked on turning HelenOS into any kernel. And Jirka Svoboda, who was not at the camp, but at the same time until today, has been working on a replacement for our compositor, the display server. So this is, let's start talking about the IPC version 2 stuff. This is a recapitulation from my talk from 2 years ago. On this picture, you can see how HelenOS IPC works. So there are some tasks that are communicating with each other. The orange one, that's a client. It has some capabilities. So it has a capability to a kernel object called a phone. phone is connected to another task's answer box. And the answer box, that's a multi-queue object which contains queues for receiving requests from other tasks and also replies from other tasks. And as you can see, we have 3 tasks communicating, which means that the blue one, which is the recipient of the orange task's requests, can either directly reply to a request or it can forward it to a third task, as is the case now. And then when the green tasks on this picture answers the request, the answer goes to the answer box of the orange task, from where the orange tasks can fetch the answer. What I wanted to mention on this picture is the fact that in this setup, in this version of HelenOS IPC, the message, which is called the IPC call, is always allocated by the kernel, is fixed size. There is a limit on the size of the buffer that can be attached to it, and is just one. Like it can be used only once, so the kernel always allocates it anew, then it's sent to all the other tasks, answered, and then it's deallocated. So you can think it's a little bit wasteful. Then I mentioned the phones, which if you have capabilities that kind of point to some destination endpoint for communication, can be understood as a little bit unnecessary, especially if you can have more of these objects that represent endpoints, which is the answer box in this case. Also, one important limitation of the HelenOS IPC is the fact that it was possible to have only one of these answer boxes per task, which is something that we were trying to fix or to limit. So 2 years ago, I raised some questions like where would the answer go if you had more answer boxes, and also how do you wait for multiple requests and also replies to an IPC. And this is something that I tried to solve in IPC version 2. It's centered around some new kernel objects, specifically an IPC buffer, which is pre-allocated by the user. So you get a capability to an arbitrarily large piece of memory that is reusable, so it's not thrown away after it's first used in the IPC. And in IPC, you basically only pass this capability to this buffer. You do not kind of allocate anything else, or you just pass the capability, basically. Then there is the IPC endpoint, which is a replacement for answer box. You can have as many as you like of these. And the third kind of kernel objects is like a cap list, which is a container for capabilities. It's something like in Mach, there is this thing called port sets. It basically allows you to have a capability to a kernel object into which you put stuff, and then you can refer to this set of objects by one capability. So how does this work in practice? So the client allocates a buffer, the server allocates an endpoint, and then the client basically sends the buffer to the endpoint. The server then waits on the endpoint and supplies a capability which is not yet associated with any object. Then when the buffer comes, the kernel makes the association. The server can put its answer into the buffer and can finish the buffer by basically replying to it. And then the client can wait on the capability of the buffer. This also answers the question of like to which answer box does the reply go. It doesn't go to any answer box. You can just wait on the handle of the buffer itself. I would like to emphasize that in this bluish area, no allocations take place. So everything is allocated in the yellow area, and when the communication takes place, everything is already allocated. And then after having waited for the buffer, the client can basically make another request with the same buffer using the same capability, and the whole thing can repeat over and over again. So this is the simple scenario. There is also more complicated scenario which involves the capability lists. So here, both the client and the server allocate a capability list, the cap list. The server immediately puts both of its endpoints, now it's using 2 endpoints, into the capability list. The client now allocates 2 buffers, and upon sending those buffers, it specifies the cap list here, which results in the kernel adding the buffer into the capability list, right? And then the server waits on the capability list, so it doesn't know which endpoint will receive data first, so it doesn't matter here, any endpoint will be okay. Then it finishes the received buffer, and then the client can also wait on a capability list. It also doesn't know which answer will come first. And then everything is deallocated and destroyed. So this was, in short, how the new IPC stuff is supposed to work. If you're interested, talk to me afterwards, or there will be a link to a GitHub repo. So something completely different, which is the AnyKernel stuff. So are you familiar with what AnyKernel is or what AnyKernels are? Yeah, I take it as yes. So for instance, NetBSD is a classic example of a AnyKernel. It's a way of structuring operating systems in a way that they can provide components that can either form a monolithic kernel or components for microkernels or unikernels. So we also Martin tried something like that with HelenOS. This time the benefit is that HelenOS is already kind of sliced into very fine-grained components, so you don't have to carve them out of a monolith, which is the case with NetBSD, and you just make some adaptation to the linking process. Maybe it's slightly more complicated than that, but you can imagine it has to do something with linking. And you can then do things like transition from this thing, which is the normal microkernel stuff. You have both the client and the server as independent tasks. Here you have kernel, and just by reorganizing stuff and making use of this component, you can basically put it in the kernel, and voila, you have a VFS server which runs inside of the kernel. This is also a work in progress, so if you're interested, talk to Martin afterwards. And last but not least is the display server thingy. So right now we have a compositor in HelenOS which provides a GUI with windows, some nice visual features like transparency and rotation. But there are also some aspects of this compositor that are being now perceived as drawbacks or maybe not ideal things. So Jirka Svoboda is working on a replacement that should eventually replace the compositor and the console server. It should also be possible with this new stuff to have something like a GUI in a text environment or in a pseudo-graphic environment, and it should be basically still the same thing. It shouldn't matter whether it's graphical or textual. I personally feel that this topic is too deep for me to talk about in this very short time. So if you're interested, I would like to refer you to this ticket 816 or Jiří's GitHub ticket, which is the well, this is the ticket, and this is his repository. So if you're interested in that, go there. And I think I'm just about to run out of time. So thank you very much for your attention.
Unfortunately, we don't have time for questions, but Martin and Jakob, Martin, they're around, so find them and ask them questions in person.